We're going to take a look at a simple low-pass filter again, but this time it's going to be a non-inverting low-pass filter. The filter we looked at last time, the input went into the inverting input. So we might wonder, how will this behave? How will it work? We know that it has a range of gains as a function of frequency. And so we'd like to know, where does it start off, what gain does it start off at, and what gain does it end off at? Well, to find out, we could do a very, very simple analysis. And let's just say that there was no capacitor here. So we're going to find out what the low frequency gain is. Low frequency gain. And what we do is we remove the capacitor. Now, if we remove that capacitor, the gain of this circuit, hopefully you remember the basic characteristics of non-inverting amplifiers. The gain of this circuit would be VO is equal to VN times R2 over R1 plus 1. So that's going to be the low frequency gain with no capacitor there. Now, for the high frequency gain, the capacitor acts like a short. The cap acts as a short. So let's imagine that for a moment, that this capacitor is a short circuit. If that's the case, you'll notice that if the amplifier is working properly, this being Vn, well then this also must be Vn. And since the capacitor is short, then this also is Vn. And that tells us that at high frequencies, VO is equal to Vn. So let's try and put some component values in and see what these numbers might possibly be. In our previous example, we had this low frequency gain being a gain of 10. Well, we're going to keep that, a gain of 10. And so to do that, we're just simply going to let R2 equal 9K instead of 10. And we're going to let R1 equal to 1K, as it was before. And we're going to let C equal 0.1 microfarads. So now let's take a look at the low frequency gain. Low frequency gain is equal to VO is equal to Vn times 9K over 1K plus 1. And you can see right off the bat, this is 10. VO is equal to 10 times Vn, and there's the gain. Now we can convert this to dBs, and you remember how to do that, or in dBs. We simply say 20 times the logarithm of 10, and the log of 10 happens to be 1, so we end up with 20 dB. So notice we have the same gain as we did in the previous circuit. Now let's take a look at the high frequency gain. High frequency gain, we have it right here. VO is equal to Vn. And we can see what the gain is. The gain is 1. Just simply 1. What goes in is what comes out. Or in dBs, we have 20 times the log of 1. Now the log of 1 is 0. So 0 times 20 is 0 dBs. Now this is interesting. When we take a look at the previous circuit, we did start off with a gain of 20 dB at low frequencies, but high frequency gain, it just kept falling off and falling off. It would go through 0, then minus as many dBs as we would want to measure. So how can we plot the response of this characteristic? Well, the first thing, of course, is we're going to do is we're going to find the corner frequencies. The corner frequency of this circuit is just the same as it was in the previous example. It's going to depend upon this C and this R2. And so the corner frequency is simply 1 over 2 pi, in this case R2C. And the corner frequency occurs is when the reactance of the capacitance becomes the same as the value of the resistance. And that's where the change begins to occur. It stops acting like a resistor and starts acting more like a capacitor, and the roll-off continues. So let's put in our numbers. 1 over 2 pi 9k times 0.1 microfarads. And this time, of course, we'll get a different corner frequency than before because this is 9k instead of 10. And it turns out to be about 177 hertz. So now we can start plotting. So let's make a little chart of gain versus frequency. That's gain in dB. And this is the log of frequency. And so we'll start off with 20 dB at the low frequency end. And then it's going to stay more or less 20 dB until it hits this corner frequency. And let's just say on our plot, for the sake of discussion, it falls right here. So at this point, the frequency response is going to fall off. And of course, we know what the roll-off rate is. It's 20 decibels per decade. So let's draw something about, let's say, 1 decade up here. Let's say this is it. 1 decade would be 10 times the frequency. So it's 1770 hertz. So there's 1 decade. It will roll off like this. Now, above this frequency, what happens? Well, at high frequencies, the gain is going to be 0 dB. Well, this happens to be 0 dB, which is a gain of 1. So it's going to level off. Now, remember in our previous circuit, it just kept on falling like this. Just kept on falling. Now, recall also that these very nice, simple straight lines that we can draw, which are known as Bode plots, are very, very, very convenient to do some very quick analysis, but they are only approximations. The corner frequency is actually 177, but the gain has dropped here by 3 dB. So remember, we drop this by 3 dB. That's the difference between the real value and the approximation. And likewise, on this curve, we're going to be up by 3 dB. 3 dB. And if we were to now draw the actual curve, it would be more like this. And this now represents the actual frequency response of this circuit. So you can see why it's called low pass, because it's passing only low frequencies and it's attenuating high frequencies. Notice also that this is the low pass response for a non-inverting amplifier, whereas for an inverting amplifier, it falls off like this. So you might wonder, does it continue like this forever? Well, the answer is no. Remember that the op-amp itself has intrinsically very high gain up here, something like 80 dBs or just tremendous gains, 100 dB, 120 dB, and it has an intrinsic roll-off. It rolls off like this as well. And so eventually what happens is that as frequencies increase, it will hit the roll-off of the amplifier itself, way out here someplace. And this, of course, would be the defined by the way the amplifier is designed itself. Its own 0 dB gain frequency. Now, you might also recognize that this circuit, like the previous one, is really an integrator circuit. And it's over this period to the slope of the curve that the circuit really acts as an integrator.